evening, as the case may be. I'm Scott Holloway, and welcome to another edition of Holloway Help. Today's topic is springs. Another common spring problem the AP likes to do is dropping a mass onto a spring. So if I have 2 kilograms, and we'll say it's 0.2 meters above the platform, and we drop it, how far is the spring going to compress, and what's going to be the amplitude? In other words, how high is it going to bounce up and down? When it happens here is they will tell us usually whether the block is going to stick to the pad or not. In this case, we're going to say it has a little bit of putty or something underneath, putty or glue. So it's going to stick when it hits the pad. So we're going to drop this distance, compress this, keep traveling down, and then oscillate up and down from that point. And we'll talk about oscillation after that. So again, I want to use conservation of energy. Ui plus Ki equals Uf plus Kf. And if I call this point my high point, call this my before, so this is my before point, and then when it's fully compressed down here, my after point, before the block we release it from rest has no kinetic energy. It only has mgh. Now h we'll have to define. H is going to be from this point all the way to here. So if we call the compression x, this h is going to be the point to it fell plus x. So this is going to be 2 times 9.8 times 0.2 plus x. That's mgh. Now, when it falls down, it's going to hit the spring, compress the spring, and this point here, it stops. So there's no kinetic energy again. So we can ignore all the changes in kinetic energy in the middle and say at the end, we're going to have all spring energy. So it's going to be 1/2 k sub s x squared. Now, we're going to have a distance x here is going to be x as we've drawn it. So it's going to be 1/2 k x squared. Now, do we have k? And the problem, they'd either give it to you and tell you what it is, and I'm going to do that now, or they'd have you solve for it using another piece of information they would have to give you. Or they would set the block on the spring and show you how much it compresses. So what I'm going to do is I'm going to say the k here is, I don't know, 450 newtons per meter. Now k's will vary between very low, like 1 or 2, all the way up into the tens of thousands, like a car spring. So it depends on what kind of springs to how high this is, but this number can vary quite a bit. So now, if I plug that in, the only variable I have left is x. All right, so what I'm going to do is I'm going to plug in 450 newtons per meter for my k, and we'll go from there. So I have, probably should have used 10, but that's okay. 19.6 is 0.2 plus x equals 450 times 1/2 over 2 x squared. Now you notice what's going to happen. I'm going to get a quadratic. And that means I'm going to have 2 solutions. I'm going to have a positive and negative solution. And so we got to look at both those solutions and figure out what they mean. So I'm going to punch this in my calculator and we'll see what we get. All right, after I plug this equation into the quadratic formula in the calculator, I get 2 solutions. I get 0.183 meters and I get negative 0.95 meters. So I said wrong. Negative 0.095 meters. So which one do we want? Well, as we drop this, what's going to happen is the object's going to come down here. Basically, the x that we measured is this x here, and it's going to drop down 1.83 meters. So this x is going to be, 0.183 meters. And that's going to be our drop this way. This negative 0.95 is after it bounces back up, it's going to rise back up 0.095 meters with the block attached. So it's going to oscillate up and down. Now it won't get as high as it originally was because the spring will be pulling down as it stretches upward. The spring's going to pull it down, so it'll be somewhere shy of the original height, and hence only 0.95. The negative is the opposite direction. We're letting it drop, so it's going to be in the opposite direction. So for this, our max compression X is going to be the positive solution, the 0.183.